Okay, guys, so we'll kick off. As I mentioned, thanks for coming to the August edition of the Sydney Databricks Meetup. We've got a great session planned today. I just have to go through some housekeeping rules. So first of all, this session is being recorded, and we'll make the recording and slides available on datadriven.com. We've muted everyone, so if you have any questions, ask them on the chat in Teams. There's a Q&A section. I'll be looking at them as Jin presents, and at the end of the session, we'll go through all those questions and have them answered. So a quick bit of blurb about what we do at Datadriven. We help people extract more value out of their data with advanced analytics and ML on Azure. Digital transformation, data strategy, implementation, that's the kind of thing we do here. Now, so our presenter today, Jin Jia, he's all the way from Japan. This is the power of virtual meetings. He's a solutions architect at Databricks. He's got a great blog, which is definitely worth checking out. It's called The Book of Architectures. I'll put the link on the slides, and as I said, I'll put those up later. There's some great content on AI, different solutions to different projects, different problems. It's pretty impressive. I highly recommend you check it out. And today, Jin's going to be sharing with us how he's made Databricks more performant with some low-level Databricks and Spark tips. So, Jin, I'm going to hand over to you now. If you want to just present your screen.
Thank you, Ronnie. Let me present my screens. Ronnie, please tell me when you can see my screens.
Yes, that's there. Go for it.
Perfect. Thank you. Hello, everyone. It's very nice virtually meeting you all. My name is Jishin, or like Ronnie introduced, I'm more commonly known as Jin, like Gin and Tonic. So in case if you bump into someone called Tony, you know who to call. I used to live in Sydney, Australia. Been living in Sydney for the last 16, close to 17 years now, before I relocated back to Tokyo as part of my work requirements. So I'm now based in Tokyo, Japan, and super great to be able to present on Ronnie's Sydney Meetup session. Today, I wanted to share some of the practical techniques that I've learned from my real-life projects and from my experimentation on how to make your Databricks more performant. A lot of these techniques you're probably going to be able to find from like books like Spark. The books talks about Spark tuning, etc. To be honest, I'm not a very theoretical person. I'm a hands-on, practical type of guy. So I wanted to condense some of the learnings I took away from the project and be able to share with you in a digested format. Hopefully that's going to make your life easier. Thank you all. As you know, I'm sure most of you are already aware of Databricks or have been heavily using Databricks. Databricks is both a company and a product. Databricks is the driving force behind many of these key data and AI open source projects or open source technologies, starting from Spark, which is kind of becoming a de facto standard to big data processing or any big data running, any big data sets of problems workload. Spark is a highly refined parallel processing engine that can work on anything from ETL all the way down to distributed deep learnings. And Databricks is also the company originally behind this concept known as Delta Lake, which brings reliability and performance to your big data sets, big data assets in Data Lake. And we also are the mastermind behind MLflow, which is the utility that helps supporting your ML lifecycle end to end. And more towards lately, Koalas, we have released a 1.0 version that went on GA, which is the big data version of Pandas. And Koalas, I think, right now covers around 70, maybe up to 80% of the Pandas API. So data scientists who are familiar with Pandas can now use Koalas in the same way they already accustomed to work on big data sets, breaking the memory limitation, etc. When I introduce Databricks to my customers or my partners, I typically like to use cooking as an analogy to talk about Databricks. I'm sure you're all very experienced and experts in this field of data and AI, particularly when creating data platform to serve ML problem or DL problems, or even just running a BI reporting dashboards. You have to typically go through a pretty long, mundane, hectic journey in order to transform your data, which I'm calling it my food, my ingredients. You have to store it according to the type of food you require in order to serve your meal, and you have to prepare your own tools, utilities, polish them, customize them, make sure that they work according to your needs. And you also have to build this collaborative kitchen or platform on which you can work, and probably not just yourself working alone, also collaborating with your team, sharing, IPs, codes, data assets, etc. And once you've got all of that ready, you also need to know how to use all of these, right? Skills and recipes is indispensable part of creating nice, tasty, delicious meal. So when you have gone through all of that journey, which, to be honest, I've been doing this for the last probably more than 10 years, creating Lambda architecture, building big data pipeline, processing data, etc. I won't be shy in telling you I hate even looking at this slide, because it just reminds me of all the nightmares and bad experience I have gone through preparing the whole data platform, data pipelines, in order to just produce one advanced analytics use case or any use case of your need. Databricks decided to, amalgamate all these necessary process but mundane overhead and abstract those away from your day-to-day work by offering so-called unified data analytics platform as a SaaS, software as a service, on cloud. And so that you can focus on just doing what you need to do. The core value, as you already know, on cloud is to accelerate your time to value. So you don't have to spend hours and hours and resources, times to develop your own platform, manage cluster, infrastructure, security, authorization, authentication, all the kind of things. You can just go ahead and spin up cluster, write your own SQL, Python, or do your advanced analytics, BI work, or ETL work as you wish, without having to worry anything about infrastructure setup, maintenance, patch installation, all that kind of things. Hence, the value is really to shorten your cycle to deliver a delicious meal and also to reduce the total cost of ownership. And also what I like about Databricks as a practical user, practitioner, I'm not a salesperson, is I can use this single platform to perform pretty much all data related stuff, from ETL, data ingestion, transformation of my data, to developing or experimenting, modeling on the data, to delivering the insights of model artifacts to the serving target model scoring system, and even sharing my notebooks, which contains the analyzed insights from the data with my users, stakeholders, analysts, etc. You can do all of that in a single platform. And so far, I think Databricks is the only practical platform that offers you the ability to amalgamate all the data-related work on a single platform with ease. So under the hood, as you know, Databricks offers these core data and AI technology, which are all open sourced already as a managed service, so that you don't have to worry about setting them up, tuning, etc. And on top, Databricks also offers lots of features, like proprietary features, UIs, to improve user experiences of using these underlying technologies when developing your own data and AI solutions. Stuff like Notebook ID, collaborative environment, collaborative workspaces. Databricks automatically adjusts the size of the clusters, and resource management and resource allocation. Towards more recently, we have this pooling and high concurrency mode introduced into workspaces, where Databricks simply manages the resource contention for you in a team collaborative context. So a lot of this is already done behind the scenes, automatically catered by Databricks proprietary algorithms and technologies. And then your data runs on top of your, the Databricks runs on top of your existing external data, but also in order to make things a little bit easier, we also created a kind of local version of the distributed object storage to serve things like storing temporary data for fast access via fuse mount, which is a technology that increases speed of accessing a common distributed objects from your cluster worker nodes. So all of that has been taken care and packed into one nicely produced, engineered piece of suite softwares. And from users' perspective, whether you're data scientists or engineers or DevOps guy, you just have to open the browser, put in your workspace's URL, and that's it. Start writing your code and start producing magics. So that's what I really like about Databricks as a user rather than as an employee. And Databricks runs on both AWS and also as a first-party service on Azure. So it natively works with lots of AWS or Azure existing data services and ecosystems. And apology, this sounded a bit repetitive to you. I'm sure most of you are already heavily using Databricks or have tried Databricks to some extent. So today I wanted to focus on my sharing my tips and learnings on how to get the best cost performance out of your Databricks. I wanted to start by talking the scaling properties of Databricks clusters. Often my customer asks me the question, hey, Jin, should I scale out my cluster or scale up my VM instances? If I do so, I know my job is going to run faster, but wouldn't it cost me more? And which is better? Should I reduce time by paying more, or should I do the vice versa, etc.? That's a really tough question, and I've always had this question myself. So I decided to create a little experiment to understand the cost performance nature of Databricks clusters. So here I've prepared an ETL job, which is not that complicated, just does kind of joins, transformation, aggregation, etc. The interesting part about this experiment is I experimented the same ETL job on 16 different cluster configuration. So I have my minimum cluster configuration setup consists of 2 workers and 4 cores, and it's gradually scaled up and scaled out to 16 workers and 32 cores. So the permutation of these 2 combinations produces 16 unique setups of Databricks clusters. And I also to make the result more reliable, I decided to run the same ETL job 30 times on each of these 16 combinations to produce a total of 480 runs of this single ETL job and measure the total cost it took to run to run the ETL jobs 30 times on each of these cluster combinations and the average job time from running 30 tests. And here's the result I wanted to share that with you. The dots means the color of the dots means number of cores I'm using for a single test, and the number means the actual number of worker nodes. And here's the result. So from 4 cores, when I scale out to 8 cores, and 8 cores consists of 2 workers, 4 workers, 8 workers, and etc. And then 16 cores, again, repeating from 2 workers, 4 workers, 8 workers to 16 workers, all the way up to 32 workers, basically doing the same. So here's 15 dots of my test. You might be wondering where's the last one, because I said in the beginning, I'm doing this over 16 combination. The one actually falls outside of the visible range of this graph, so I decided to omit it because it sits somewhere here. The line here is the best fit line that describes the characteristics of each of these cluster test results. So I know this looks a little bit busy, so I created a summary version for you and wanted to share my insights that I learned from it with you. Firstly, this little curvy line represents the general behavior of, or general cost performance behavior of a Databricks clusters. So when you scale up and scale out, what you notice is expectedly your job time is going to gradually reduce, of course, and then your cost is going to proportionally, or more or less proportionally, increases. There is a sweet spot, however, somewhere around here that says your job runs in the least amount of time and costs you the least amount of money. If I go back to my earlier experiment result, you'll quickly be able to spot from this result that this cluster configuration, which is blue represents 16 cores, and number 4 means using 4 workers. This particular cluster configuration had the best cost performance for running my ETL job, because it not only achieved, well, maybe not, not the fastest one, because it took around 20 minutes, as opposed to some other results, which is less than 20 minutes, but it gave me the least amount of cost. So I think, personally speaking, I would favor this cluster configuration to run this particular ETL job, because I think it gave me the best balance between the cost and the performance. Now, coming back to the summarized version of learning from this experiment, I found typically when you scale up your VM instance, what it does to the cost performance curve is it kind of pushes towards the left top corner. I mean, I'm exaggerating the effect a little bit with animation here. The effect is kind of subtle. However, you can I have repetitively observed when you scale up instances, the curvy line, the CP line, moves towards left and up, which is nice. So when you are starting fresh with your workload, I typically advise customers to start with scaling up your VM instance, and there's good reason attached to it, which I'll cover in a minute. But first, scaling up your VM to a moderate size. I'm not saying spending all the money on getting the world's best VMs. It's likely going to be a waste of money. But set it to something moderate to start with. You'll likely get a pretty good result just by doing that. And when you scaled up your VM instances to an extent that it reaches a flex point, and what I mean by flex point is further scaling up doesn't necessarily bring any added benefit, marginal benefit to your cost performance, i.e. you're not reducing your job time much, but your build, your cost is actually increasing a lot, then this is when you should consider about scaling out. And what scaling out does, from learning from the experiment, is it actually moves your CP performance nicely and smoothly along the CP curve, right, as animation is indicating. So combining these two learnings, my recommendation to start off when you pick up a Databricks cluster is pick a moderately sized VMs and starting small in numbers. And when I say small in numbers, typically range between 2 to 4. Again, this is very high level generic guide, because every single use cases are different. You may be dealing with terabytes or even petabytes of data, and and working with that scale of data on 2 to 3 workers is nonsense. So consider this as a very high level general advice. Starting small, starting with a moderate sized VMs on a small number of clusters. This is because when you have a larger number of instances, worker nodes, you are increasing the overhead on managing those workers from driver nodes perspective. And also when Spark distributes data, it has to use bandwidth, network bandwidth, and hence you're increasing lots of overhead managing large number of workers. So I typically don't favor scaling out that much. I favor scaling up as a starting point. And when you start to notice that diminishing marginal effect or marginal benefit, that's when you should scale out in order to move your CP cost performance along this nice CP curve, so that you can potentially gain more benefits, maximize your per dollar investment. And when you are in this region, this is really a business question. Are you willing to pay twice as much in order to reduce 5% of job? Maybe the answer is yes, maybe no. So when you are in this realm, this area, this becomes highly business relevant, business related, business driven questions. But to start off, you can adopt this strategy or recommended practice to increase your overall performance without paying much. Right, so that's about the cluster. And as I previously mentioned, I prefer choosing a cluster with fewer larger instances over a cluster with many smaller instances, because you might be incurring an added overhead of managing worker node, lots of worker nodes. And also, if you don't know how many workers to set as a starting point, you can probably pick one of the most important or prominent jobs workload that you plan to run, and run that with a small amount of test data to understand how many tasks as in Spark task, Spark is using in order to accomplish your ETL work or any workload. And that gives you a good indication of how many workers I need to set. And this is a reason why. Breaking down Spark's execution. When I say execution, it's not a formal terminology. I simply refer to a chunk of code that you want to execute. And when you execute a Spark job, it breaks down into a number of jobs, Spark jobs. And each job is roughly a correspondence to a number of actions the Spark need to perform. As you know, Spark is a lazy evaluation system, so that it doesn't perform action immediately when you finish writing your query. It only performs action when you trigger some kind of action, which I'll cover in a minute, to perform the predefined logical transformation logics or code. So your number of jobs corresponds to number of action you defined in your code. And the Spark jobs can be further broken down into stages. Stages means how many times your data need to be shuffled among your workers, and one stage corresponds to one shuffle. And the lowest level of your Spark job composition is called a task, and task is basically number of RDD partitions, and I'll cover that in a minute in detail. So your large job and data itself is divided into smaller chunks, and that number of smaller chunks typically matches number of CPU cores you have in your cluster on your worker nodes, to be precise. Hence, if say for argument purpose, if your ETL jobs requires 125 partitions or tasks, then you probably want to set your vCPUs to be something around 128 or the factor of that numbers to maximize parallel processing as a high-level guidance. And also, this is quite obvious, but depending on what type of workload you're planning to do, choose the specialized type of VM instance for your workload according to the nature of your workload. For instance, compute optimized on AWS, that's going to be C series. On Azure, it's F series. You typically get more CPUs allocated per gigabytes of RAM, and that's super useful to disk IO heavy operations when you have to rewrite in a frequent manners and thousands of operations, concurrent reading and writing at the same time using Parquet. And Parquet is highly efficient in reading, but quite heavy in writing because of the snappy algorithm. You have to compress and decompress when writing and reading the Parquet data. So for those type of workloads, a compute optimized sets of VM might be the best choice. On the other hand, if you're running a large amount of, iterative data analysis or developing models, you appreciate having more memories compared to number of CPUs. I mean, in some cases, especially in deep learning, you don't even really care about CPUs. It's more of a GPUs world. And on the other hand, if you're not sure where to start with, I think I need to get a balanced set of CPUs capability and RAM memory capability. I always recommend starting with storage optimized series or general series, especially when you use storage optimized series. You are by default enabled and customized optimized, to be honest, to use Delta Cache. And Delta Cache is a technology that can drop a local copy of your remote data so that your subsequent read access to the same sets of data or subset of data will be much, much faster. And on a storage optimized VM, on both AWS and Azure, you get NVMe SSD, which is super fast. I think if I remembered it correctly, it can achieve something like astonishingly high number of astonishingly high read performance on SSD. So if you don't know where to start, I recommend starting with storage optimized VMs. Okay, so we've been talking a lot about cluster, and I hope what I've learned in my real life has helped you at least have a starting point guideline to, configuring, setting up your clusters for your own work. I wanted to move on to how do you maximize parallelizing your work to get the best ROI on your clusters. We all know that Spark is a parallel computing framework, and by parallel, it really means dividing and conquering your large amount of data or large heavy amount of work. This illustration shows, let's say I have 8 workers, and these dots represent a partition of your data, like a small chunk of your data. If the data is distributed evenly across your worker, that's perfect. It's the best you can ever imagine on a parallel computing systems. However, in reality, it's not always so nice. You might have a lot of data concentrated on single machines, or you have not so evenly distributed data amongst your worker nodes. Some worker is working on a data which is 10 times larger compared to the average of the rest. And sometimes you might have a VM which is pretty much sitting idle without leveraging its capabilities. And that's really bad for obvious reasons. An ideal size of a partition, RDD partition, to use the formal terminology in Spark, is around 200 megabytes. And this is basically considered as a best practice. And I think the number is derived from thousands of experimentation on both small sets of data and as well as large sets of data. So I typically go ahead. I won't be strictly bound by 200 megabytes, but I'll start. This is a good starting point for me to know, okay, if I'm going to partition my data, I should aim to make it a single partition to be around 200 megabytes. And then I can distribute them evenly onto my worker, and precisely speaking, onto my worker's vCPU cores. Another reason distributing your partition evenly is super important can be described by this queuing problem. Assume that I have my data divided into 9 pieces, 9 dots, and I have a worker cores that has worker node that has 8 cores. If I let Spark do its own magic, what Spark will do is it will just distribute the first 8 dots, 8 portions of data onto 8 cores. And let's say each of them takes 10 seconds, more or less around 10 seconds to complete. Now, you notice that there is a little guy being left over, which is the 9th partition representing the last bits of my data. And as soon as these 8 partitions data get processed, my last one get added to whichever got the bandwidth to process another set of data first. And then, assuming this data set also takes 10 seconds to process, you'll be looking at 20 seconds as an overall processing time for dealing with your for dealing with a problem, which is really bad because it could have been shortened to 10 seconds, but because of this little tiny 1% of the data being left over, you have effectively doubled the amount of time for your parallel processing system to work on this particular problem, which is super bad. In order to, I hate showing you this slide. In order to find out what are my ideal RDD partition numbers, I have actually created a formula and posted on my blog. But today I'm not going to be talking anything about formulas or math. Instead, let me move to my Azure Databricks environment, and I'll show you a very simple way of calculating what are my ideal number of RDD partitions so that I can increase the efficiency of parallel processing. Right, here I've got a sample dataset, which is, let me make it easy for you, which consists of 5 columns of random floating numbers, and the total amount of records is 100 million, which is not that big, but it's not small either. I'm going to be reading that data, and because it takes around 25 seconds, I'm not going to be running it here, but I know if I read in that data, which is seemingly quite easy to work with, and simply perform a count would cost me 25 seconds on the 100 million rows of data. This is pretty bad, to be honest, on a Spark. And Spark is known for its fast in-memory computation. The reason why this is so slow is because I have, actually, let me show this to you. I have deliberately divided the data into 3,000 pieces, which is a pretty high number, considering my data is only 100 million rows. So that's why it's small, and which is the queuing problem, the unbalanced distribution of data partitions problem, which I showed you earlier in my slides. So let's focus on how to quickly fix that. Firstly, I will need to check number of RDD partitions currently being used by my Spark, which is 125. And the reason I know that is I've used these things called rdd.getNum partitions. If I run this on the data set, which consists of the sets of transformations I wanted to perform, I can understand how many partitions Spark decided to use. I can also check that from, say, earlier when this count syntax. If I expand my Spark jobs, I know there's 2 jobs consisting, and like I mentioned earlier, each job corresponds to a action. So here we've got 2 actions because I'm first clearing my, because I'm doing a performance benchmarking, so it's a good idea to clear my Spark catalog cache, which corresponds to job 0, and my second one is corresponding to the count operation. And I can see Spark has divided my job or data into 125 pieces, and that becomes my RDD partition number, which is set automatically by Spark. And in the later version of Databricks, it actually gives you some tips on how to fix a problem because it has detected an obvious slowness in the performance, which is good. But today we're not going to be doing this easy fix. I wanted to show you how to manually fix the problem and show you why is it a problem. So first I get the number of RDD partition, which is 125. And you can also check the Spark UI to get the same results. And then I need to also understand my RDD partition size. The trick to do that is, again, I'm defining exactly the same transformations and storing that to a variable called df. The trick is to cache it, then say take 1. And what this does is I'm forcing this operation to be cached in memory, and I'm forcing my Spark to return me just a single RDD partition. As you can see, I'm only getting 1 result. And from there, I can open up my Spark UI to go ahead and, it's here. I can go ahead and check my input size and records. So in this case, the input size is 34 megabytes. And I don't even know how to read it properly. I think it's 800,000 rows of data. So if I do a quick math, 800,000 rows times, I know Spark is dividing that by 125 RDDs. That gives me 100 million rows, which is correct because my data set is 100 million. So I know a single RDD partition is around 34 megabytes in size. And there's also alternative, and I'll be sharing my sample demo notebook with you so you can try it later. And that's the purpose of me creating this sample notebooks. There's also another easy way to find out your total dataset size, which is simply by looking at your directory that contains the Parquet data. So if I simply run that, I'll get some high-level stats. For example, this directory, which is my Parquet data, consists of 3,000 files, individual snappy Parquet files. because I used repartition 3000 to divide my data into 3000 pieces deliberately. So this is correct. And you can also tell me how what's the total size of my data set, which in this case is 4.3 gigabytes. Perfect. So you can use either method 2 or method 1 to work out your total dataset size. And why is that important? I've created a little form here for you to capture those information and work out the ideal number of partitions. This is super simple. First, you put in amount of RDD partitions you have, and then you put in the single partition size in megabytes, which is around 34. And if I times these two together, 34 times 125, it gives me 4250, which is around 4.3 or maybe 4.1 gigabytes of in size. As you can also get more or less similar results from using method 2, whichever you prefer. And then next, what you need to do is calculate ideal number of partitions, because I know it's recommended to set my RDD partition size to 200 megabytes. So if I divide these two numbers, I'll get, divided by 200, more or less 21.25. And this is going to be my ideal number of partitions I need to set. If it's less than 1, obviously you can't set up half partition, so you have to round it up to 1. But I don't have 21 CPU cores in my cluster. In fact, I'm using 40 cores for this experiment, and I know each worker has 8 cores, and I have 1 driver node, and driver node typically doesn't perform work, so I know I have to subtract 8 from 40, so my actual worker node CPU is 32. So my worker node cores is 32, and here it says you need to take a factor of this number that is also closest to 5, which is this. What it means is it's always good to have whole number integer multiplication of your total worker node cores to run your job on, so that we are evenly distributing our data sets onto our worker nodes. Therefore, in this case, 32 appears to be the number which is a factor of my total worker node cores, which is also closest to the ideal calculated number of partitions. So it's going to be 32. Right. And then I can fix my problem by saying, okay, I know 32 instead of 125 is going to be the best, most ideal number of partitions. So I'm going to use repartition to resize my Spark calculation. Now, in this case, I'm also writing this out and saving on a DBFS, but you don't really have to do that. I'm only doing this so that I can reuse the group partitions, I'm calling it, the fixed partitions, which is more performant. If you run a display dbutils ls command, you'll be able to see that I have in this group path, which contains the repartition results, has 35 rows, of which the first 3 rows are just committed files, some internal transaction logs, etc. And which means I have 32 individual Parquet file consists of my 4.3 gigabytes of data. Let's now rerun this and see how fast it is. Oh, actually, I forgot to warm up my cluster, so it's attaching my notebook context to the cluster, and this is going to take a couple of seconds or maybe up to 10 seconds. So performing exactly the same query, which is reading the data and simply doing a count. My apologies, I should have warmed up my cluster earlier. Okay, finally ran 1.5 seconds. And this is executed after I cleared all the caches from my Spark catalog, just for fairness, right? So compared to 25 seconds, this is 1.5 over 25, 1 divided by 0.06, which is roughly 16 to 17 times faster. And this is how you derive the ideal number of RDD partitions for your very specific problems. And I've also summarized the steps in this slide, which I will share with you later after this session. due to time constraints, I've actually packed quite a lot of knowledge and information and tried to share as much as I can. So I'm going to increase my pace. The other thing that I wanted you to be aware of is shuffling. You know that in Spark, we have two types of transformation. One is narrow transformation, and the other one is wide transformation. I think the animation pretty much says, clearly explains what narrow transformation is. Basically, your work, your RDD partitions that are assigned on a single worker node can be completed within that worker node. So before shuffling, you have, let's say you have 3 partitions, then after shuffle computation, you still get 3 partitions, and it's a one-to-one mapping, one-to-one calculation. So it's called a narrow transformation. A typical example would be selecting columns, filtering data, counting data, or creating a derived calculator columns using expression, etc. In contrary to narrow transformation, you also got a wide transformation, which is basically copying your partitions and then distributing across your entire worker node. And this is necessary because sometimes we need to perform aggregation, we need to perform sorting or distinct counts. And obviously, for obvious reasons, single worker node cannot perform sorting by itself alone. So you have to have the copy data, or for example, when you join in two datasets, you have to have a duplicated data being distributed onto your worker node in order to perform the joins, and that is called wide transformation. And when wide transformation happens, your RDD partitions numbers typically increases because Spark needs to create a copy of that and then distribute it among your workers. This size is actually set by Spark, but not automatically. In pre-Spark 3.0 era, this is a fixed number controlled by Spark SQL Shuffle partitions settings. My recommendation is, I'm sure you already get this message, is to set the size according to the total number of CPU cores that you have from your cluster. And you can use the syntax sc.default parallelism to know the number of CPU cores you have on your worker node, and then times n being a positive integer greater than or equal to 1, to set your SQL partition shuffling size to match a factor of the total worker CPU cores. And that typically gives you a boosted performance because, again, we are killing the unbalanced, not evenly distributed partition problem similar to the one I demonstrated to you earlier. This 200 default size is a kind of compromise midway point between smaller sets of data and really large scale data. So it's not a single answer for all. And I typically like to set this Spark SQL Shuffle partition manually to suit my own problems. And this, simply by setting this to default parallelism times 1 or times 2, will typically gives me a pretty good performance, as opposed to leaving it as a default 200. Way too large for small sets of data. And when I say small sets of data, I'm talking about in the realm of tens of maybe 50 gigabytes of data. It's considered not that big. In a Spark 3.0 or Databricks Runtime 7.0 plus, Spark has released a new automated shuffling or partition size calculator called Adaptive Query Execution. Now, without getting too much into the details, I'm hoping I can do a demonstration on this with you next time, but probably I'll save it from any details today. This AQE will automatically set the number of ideal partition size for you and also adjust the shuffling size for you. Now, that sounds super good, right? Although I haven't personally put that into a rigorous testing or been using AQE against petabytes of sets of data, but from what I can observe from my own experimentation, this AQE may not always guarantee to deliver the best performances. Hence, doing these manual calculations, if you've got the time and if you're really suffering from performance problem, doing this manually will typically outbeat the automatically adjusted performance. And here's a reason why. Let me show you a quick example. I'm sure I've opened it else somewhere. Apology for this to be in Japanese. And basically, this notebook is identical to the notebook which I've just shown you in English, except this one is written in Japanese. I'm doing pretty much the same, using the same cluster, except this time I'm using Databricks Runtime 7.2 as opposed to Databricks Runtime 6.6, which by default doesn't have AQE enabled, or doesn't even have AQE on a pre-7.0 runtime. And if I run the same calculations, and let me show you where, okay, here we go. It says 64, as opposed to when we did this test earlier using 6.6, it was divided into 125. And you notice that AQE is actually taking control of how many IDD partitions you need to use. And I'm not doing group by or join this time, but if I did that, you notice the shuffling size get automatically adjusted. But again, we know the best number according to our calculation is 32. It is not necessarily matching the best result. So AQE is helpful, but not necessarily guaranteed to deliver the best results. Okay, I also wanted to talk a little bit about partition on disk, and I'm going to increase my pace. And we all know partition can be quite confusing in Spark because so far we've been talking about RDD partitions, which is the data divided and distributed when Spark runs computation on the fly. There's also another type of partition, which some people call hive partition or disk partitioning or partition on disk. Whatever the name is, it simply means physically dividing your data by partition keys, which is conceptually kind of similar to databases indexes or primary or secondary indexes. You're basically physically dividing your data according to your partition keys, right? So this is year and month as a partition key, and I'm dividing my data accordingly. This has a very good benefits of improving the read performance because you don't have this. For instance, if I have a query, which I'm only interested in analyzing on a subset of data, 2018 January, I can instruct by partitioning on disk. I can instruct Spark Catalyst Optimizer, which is the query optimizer or query planner, to skip all these irrelevant data so that I can drastically improve, substantially improve my reading time. And if it's so good, why don't people just keep abusing them, right? Setting every single column onto partition key. I'm sure you understand the reason this is super bad, especially in an MPP or distributed parallel computing system, because if you over fine-grain your partitioning your data by partitioning them by using 10 columns or more, you are actually facing a large amount of small files, and we call it small file problems. And each file is so fine-grained, it becomes so small that your compression efficiency drops, especially when you're using Parquet, which is a recommended data format on Spark. The compression simply means nothing. And we're also increasing the metadata for managing all these small files. Your disk I/O increases, not to mention your driver node becomes more committed just by looking at the data or sorting the files and distributing them among your network. This is very inefficient and also can cause a very serious queuing problem when your cluster is small in size, i.e. you have a very few number of CPU cores. It can literally kill your parallel processing system. It's the #1 no-no to do in a Spark world, MPP world. Then again, I like to calculate what's my ideal partition file size or number of ideal partition files, right? Using an example, let's say I'm partitioning my data by year. My ideal number of files can be derived by the following. #1, because if the data is stored on data lake, which is HDFS-based storage, the Hadoop is designed to have a single block at size of 128 megabytes by default. And you need to match, or ideally, we need to match a single partition file to that size, more or less around 128 megabytes if you could, because the more you can match the size, the less amount of blocks, like physical blocks, HDFS has to scan in order to get your data. And then your number of partition files should ideally match a factor of the total worker cores. I think we've been repeatedly emphasizing this concept a lot. Whenever you divide something, you need to divide the end result need to be the factor of the total worker cost in order to get the best parallel performance. Using an example to show you what this means, say I have a 1 terabyte of 12 years of log data, or whatever the data that is, and I'm partitioning by year and month. I'm using 64 cores with A workers. If I partition by year and month, then in a simple calculation, dividing 1 terabyte by 12 years and 12 months in each year, I get 7.1 gigabytes per year and per month. And when Spark write the data out, it by default distribute, as I mentioned earlier, it distributes the data according to the number of worker cores, CPU cores you have. In this case, is 64. So your 7.1 gigabytes data will be divided further by 64 and producing a file which is roughly 111 megabytes in size. And this is pretty good because it's really difficult to match 128, but anything beyond 100 megabytes and less than 200 megabytes, I typically consider that to be pretty good size to have. So in this case, this is a good partition example. Let me show you a bad one. Without running it, let me show you pretty bad examples, which I have. Okay, partition on this bad example. Again, my apology for I originally created this notebook in Japanese and I really didn't have time to translate back to English. Here I've created 10 million rows of sample datasets randomly generated, which is basically meaningless data. When I first ran a query, this is my simple query, filtering by year, month, and region, and group by, doing some sum and average. Very straightforward. On the non-partitioned datasets, which is I'm simply writing out without partitioning, this query returned results in 1.28 seconds, which can be further optimized to run in a sub-second, but this is okay to start with. And when I check my query plan, I know it's not using partition pruning because I haven't set any partition. Now, running exactly the same query again, this time on a partitioned dataset, again over the same datasets, I'm partitioning that by year, month, region because my filter is using year, month, region. So if I partition that by these 3 columns, theoretically I should get really good results, right? At least from database or data warehouse where that applies. However, you may be surprised that this time running the same query over partition data, it actually costing me 1.8 minutes, which is more than 10 times compared to the earlier, sorry, actually more than 20 times compared to the earlier result. Why? And if I run query explain, I can tell somewhere that it says partition filters. Here we go. I can tell my query plan is actually successfully applying partition pruning. Then why my query is so slow? This is why small file problems can be so bad to any parallel processing system, because in this case, without doing the detailed calculation, I have actually divided my data into such a small, large amount of small pieces that each piece is, if I remember correctly, each file is around 15 kilobytes in size. And that's bad. And I've actually successfully triggered all these problems and therefore degraded my Spark's performance by, I don't know, 20 times or maybe even close to 30 times compared to not even partitioning that data. This is something that I want you to be very careful of. And as much as many of you might have learned since Spark 3.0, we have a dynamic partition pruning technologies enabled by default. However, in contrary to the name, you might think, oh, this will adjust partition pruning automatically for me. Unfortunately, it doesn't. It's quite something else. This DPP technology is developed to support scenarios, very specific scenario called a star schema join. When you join a large fact table with a dimension table and you have a partition on your dimension table, this DPP can effectively leverage broadcasting mechanism to distribute your dimensions partition over across to fact table so that these two schema join can become much more efficient. Okay, I know we are running short in time. I have actually included a few slides to talk about Delta and how using one optimized command in Delta can fix a lot of these small file problems or adjusting RDD partition problems. But I'll leave that to you. I'm sure you all heard Delta, and Delta really makes our data platform, big data problems, managing the problems much easier. Last but not least, I wanted to point out the use of Spark Cache. Spark Cache can sometimes be a very bad thing to do, especially when if your data size is large. And here's the reason why. Number one, if your data sets becomes very large and it doesn't fit into your worker's memory, it causes disk spilling. And depending on the work use cases, disk spill is actually quite good in some cases, but in most cases it's considered bad. So only use cache when it makes sense, and especially when your data sets can fit into your memory and the data set need to be repetitively called afterwards. The other thing I wanted to make you aware is cache is a lazy transformation, which means when you create a cache on top of your data frame, it doesn't run immediately. It only runs when some action is called upon the data frame, which has the cache enabled. And cache not only stores the data or subsets of data, it also stores the query plan, the computation logic behind when the data frame itself was created. And this is quite interesting because cache is managed by Cache Manager, which happens before the optimizer kicks in. What this means is, I'll show you with an example. Here I'm reading a simple data, parking data, into my data frame, and I'm doing a very simple filter, column 2 greater than 0, and I'm appending cache to it. So I'm effectively telling Spark to cache the subsets of this filter result in memory. Which one of these following three do you think, if I run, would effectively leverage my cache? No, without because I can't hear your answer. So I'll tell you the answer straightforward. It is only number 3, filter column 2 greater than 0 will leverage that cached result, because if you look into the query plan, only this has analyze plan, which is identical to the cached analyzer plan. All the other two will differ slightly. And although when your optimizer runs, all these 3 results, queries, would have identical or very similar query plan, which effectively delivers same performance. However, because cache is leveraged before optimizer takes place, and the cache is based on analyzed plan, you need to kind of make your query almost identical to the cache result in order to reuse or effectively leverage the cache subset. So in this case, if I rewrite the second query to something totally silly, so I'm basically on second query, I'm saying column 2 greater than 10. I'm dividing that or breaking that into filter column 2 greater than 0, and then filter that by greater than 10. In this case, this query will reuse the cache result because the first part, which is where my mouse is pointing, is identical to the cache query analyzed plan, and therefore the cache will be reused. Many people doesn't quite aware that fact. They think caching, and the cache is not free. It takes a lot of amount of time to put your data from disk on into memory. That takes quite a lot of time to do. And also thinking that after doing the query, I might be able to speed up my subsequent query because I'm pretty much doing the same. No, it's not. So you need to be super careful when using cache. Okay, my apology for running a bit over time, and thank you very much. I hope this session was useful to all of you. Back to you, Ronnie. Thank you.
Thanks all. So are there any questions for Jin while you got the expert on the line? We've got one now. How long does Spark keep the cache data in memory? Do we need to tell Spark if we don't need that cache anymore? Jin?
Thank you very much for that question. The Spark cache is kept as long as your cluster is live. When you shut down your cluster, the cache is automatically purged. And you can also force Databricks Manage Spark to forget the cache by using a specific command. You can control when to delete the cache, but if you don't, cache will be dropped when the cluster terminates.
Thank you. Do we have any other questions while we've got John on the line? I'll just give it a few minutes or two. Jen, I know we personally have faced the small file problem a few times. The most latest being on a customer that's using Databricks on a data lake, and we're ingesting a whole lot of IoT files, which we're storing in the raw zone and in JSON format. And reading those files is really painful. So we've implemented Delta Lake to solve that problem. And we had to tune that as well to get around those partitioning issues that you mentioned. But that was really interesting.
Oh, that's great to hear. Thanks.
Okay, I think we'll wrap it up now. I think there's some really good content. If we can get Jin back for another session later in the year, that would be really awesome. Jin, thank you very much for taking the time out of your day to share this knowledge with us. I think your slides are really good, and your presentation was really useful. So thank you very much. I'm sure everyone agrees.
Thank you. It's my pleasure.
All right. Cheers all. Bye.